On the night of the 21st of June 2025, a telescope on a mountaintop in Chile photographed something that, as far as anyone on Earth knew, did not exist. Nobody noticed. The telescope was not hunting for it. It was not officially working yet. It was in a testing phase, pointed at a routine patch of sky, checking its own optics and software the way a new instrument does before anyone trusts it with real science. 10 days later, a different survey telescope in the same Chilean mountains reported a fast-moving point of light and set off a global alert, only the third confirmed object from outside our solar system in all of recorded history. Then someone thought to go back through the forgotten test images. What they found there started a chain of measurements that ended almost a year later, with a claim that should stop you cold. This object is older than the Sunday, not slightly older, possibly more than twice the age of our entire solar system. So here's what the next half hour is actually about. What was hiding in those calibration frames? Why the James Webb Space Telescope measured a chemical fingerprint in this comet that matches nothing we have ever found at home? How you put an age on a lump of ice with no rings, no fossils, and no return sample. And where the honest edge of that claim really sits, because it is not where the internet says it is. You're watching Beyond the Signal, where we follow the evidence to the edge of what science knows. If you want more stories where the sourcing is left in instead of stripped out, subscribe and stick with me for this one. Start with the thing that makes this rare in the first place. Almost everything we have ever studied in space, we studied from a distance. We photograph stars. We measure light. We build models. But we have never held a piece of another star system in our hands. And until very recently, we had never even watched one go by. That changed in October 2017. A survey telescope in Hawaii picked up a small, fast object on a path that made no sense for anything born here. It was named Oumuamua. It was strangely elongated, it showed no visible coma, and as it left, it sped up slightly more than gravity alone could explain. That tiny extra push fueled years of speculation online. Most astronomers concluded it was most likely gas venting from the surface, a normal comet process that was simply hard to see directly on an object that faint and already on its way out. 2 years later, in 2019, an amateur astronomer named Gennady Borisov found the second one. That object, 2I, Borisov, behaved like a textbook comet. It had a coma, a cloud of gas and dust around its icy core. It had a tail. It was easy to compare against comets that formed right here, two objects, two completely different first impressions. And no way to tell which one was typical. Then came the 1st of July 2025. A NASA-funded survey called ATLAS, the Asteroid Terrestrial Impact Last Alert System, reported a moving object from its telescope in Rio Hurtado, Chile. The first label was technical and forgettable, C 2025 N1. Within days, the orbit told the real story. Astronomers describe the shape of an orbit with a number called eccentricity. Below 1, the path is a closed loop and the object comes back. Above 1, the path is open and the object never returns. Most comets we track sit just under that line. This one came in at roughly 6.14, the most extreme value ever measured for an object passing through our solar system. It was moving at about 137,000 miles per hour when it was found, still out near the orbit of Jupiter. The sun's gravity was never going to hold it. It was named 3I Atlas. Third, interstellar object, discovered by Atlas. Here's the part most coverage skipped. The July 1 report was not the first time the object had been recorded. Once astronomers knew where to look, archives around the world got searched. Older Atlas frames and images from Caltech's Zwicky Transient Facility in California turned up detections going back to the 14th of June 2025. NASA's TESS Planet Hunting Telescope had also swept over that patch of sky in May. So the comet had been quietly writing itself into our data for weeks, it just had not been read yet. And that brings us back to the mountain. The NSF DOE Vera C. Rubin Observatory sits on Cerro Pachón in Chile, chosen for dry air and dark skies. Its main mirror is 8.4 meters across, roughly 27 feet, and behind it sits the LSST camera, the largest digital camera ever built for astronomy, at 3,200 megapixels per shot. In June 2025, none of that was in normal operation. Rubin was in commissioning, running what engineers call science validation. It is a dress rehearsal. You point at various patches of sky not to discover anything, but to test focus, calibration, tracking, and the software pipelines that will eventually process terabytes a night. On the 20th of June 2025, the first night of that validation survey, Rubin turned toward a small region of sky. Sitting in it, undiscovered and unannounced, was 3I Atlas. After the July 1 announcement, a team led by astronomer Colin Orion Chandler working across the University of Washington and the LSST collaboration with more than 300 co-authors, went digging through that commissioning archive. They recovered detections starting June 21, 10 days before the discovery report, when the object was still 4.5 astronomical units from the Sunday, roughly 420 million miles out. Rubin kept catching it, sometimes on purpose and sometimes not. Through July 20, they pulled 49 usable images out of that window. Some frames had to be thrown out because the telescope was mid-alignment, or the comet blended with a background star, or the focus was off. This was test data, after all. Doing science with it was not simple. Rubin's automated pipeline for fast-moving solar system objects was not running yet. The team had to build custom tools to measure something that would eventually be routine. What came out was worth the trouble. Their paper, published in the Astrophysical Journal Letters in 2026, reported the earliest high-resolution evidence that 3I Atlas was already active. The coma was there, visible, months before perihelion, at a distance where many comets are still dormant. Over the observation window, the apparent size of that coma grew by about 58% as the object fell toward the sun and warmed up. They measured positions across Rubin's 6 color filters with a typical precision of about 70 milliarc seconds. That sounds abstract, so anchor it. A milliarc second is 1,000th of a 60th of a 60th of a degree. On fixed background stars, Rubin does even better, around 3 milliarc seconds. The difference is not a flaw. It is what happens when your target is smeared slightly because it is moving across the sky while the shutter is open. 2 details from that data matter more than the rest. The first is what they did not find. No non-gravitational acceleration, no unexplained push, no deviation from the path gravity predicted. Whatever else this object was, it was falling exactly like a rock made of ice should fall. The second is stranger. The dust tail pointed toward the Sunday. Normally that is backwards. Sunlight exerts a small but real pressure on dust grains, which is why a comet's dust tail generally streams away from the Sunday. A sunward-facing feature, sometimes called an antitail, is uncommon but not unheard of, and it has been documented in other comets. The explanation in the paper is something called anisotropic dust emission. Unpack that. Anisotropic just means uneven, not the same in all directions. If a comet is not shedding dust evenly from its whole surface, and if some of those grains are large and slow enough that sunlight barely pushes them, the visible shape of the dust can end up projected toward the sun from our viewing angle. The rotation axis of the nucleus can amplify the effect. Unusual, yes. Unexplained, no. Keep that distinction in mind because it comes back. So Rubin gave us the shape, the timing, and the earliest hard proof of activity. It could not tell us what the object was made of. For that, you need a completely different kind of instrument. On the 6th of August 2025, the James Webb Space Telescope pointed its near-infrared spectrograph at 3I Atlas. Spectroscopy is the tool that separates a picture from an identification. Instead of recording how bright something is, it splits incoming light into fine wavelength slices. Molecules absorb and emit at specific wavelengths, so those slices read like a barcode. Point it at a coma, and you can list what is boiling off and roughly how much of each. The barcode came back with familiar ingredients: water, carbon dioxide, carbon monoxide, water ice, carbonyl sulfide, a sulfur compound that would smell awful if you could stand there and breathe it. Nothing exotic, nothing engineered. The ordinary chemical vocabulary of comets. The proportions were the problem. Webb measured carbon dioxide against water at a ratio of about 7.6 to 1, among the highest values ever recorded in any comet, and well off the trend line astronomers had built from decades of solar system observations. That ratio is not trivia. The mix of ices a comet locks in depends on how cold it was, where the comet formed, and how much radiation it absorbed. A wildly different ratio is a hint that the nursery was wildly different. A hint, though, is not an origin story. To get an origin story, you need isotopes. Webb came back for that in December 2025. By then, the object had rounded the Sunday. Perihelion, the closest approach, happened around the 30th of October 2025, at roughly 130 million miles, just inside the orbit of Mars. Earth was on the far side of the Sun at the time, which is why the comet vanished from ground-based view for weeks. It reappeared in early December, and on the 19th of December 2025, it made its closest pass by Earth, about 170 million miles away, nearly twice the distance from here to the Sunday. There was never a moment when it posed any hazard to this planet. That pass mattered scientifically for one reason. Solar heating had turned ancient ice into a bright, gas-rich coma, and a bright coma is a readable one. Webb observed on December 22 and 23, 2025, with ALMA in Chile taking complementary measurements to pin down how fast the gas was expanding. This time, the target was not just water and carbon dioxide. It was their rare variance. Here is the concept in plain terms. Most hydrogen atoms have a single proton. A small fraction carry a neutron as well, making a heavier version called deuterium. Most carbon is carbon, 1,2. A small fraction is carbon, 1,3. The ratios between light and heavy versions get set by the temperature, the radiation, and the chemical history of the place where the material formed, and then they mostly stay locked in. That makes them a clock and a return address at the same time. The deuterium result was extreme. Webb measured a deuterium to hydrogen ratio in the water of about 0.98% with a small uncertainty. Solar system comets average around 0.029%. That is roughly 30 times higher, and statistically it sits about 15 standard deviations away from the comet population. It is higher than young protostars in our galaxy. Within our own solar system, only the atmosphere of Venus beats it, and Venus got there by losing its lighter hydrogen to space over billions of years. The carbon told a parallel story. Webb found 12C, 13C ratios in the range of 141 to 191 for carbon dioxide and 123 to 172 for carbon monoxide. For comparison, essentially everything measured in our solar system, from Martian carbon dioxide to methane in Jupiter to meteorite carbonates, clusters near 89. Our sun sits near 93. That gap is the whole discovery. Carbon, 1,3, accumulates in a galaxy over time. Generations of stars live, burn, die, and enrich the interstellar medium. A cloud that formed early, before much of that enrichment happened, is carbon, 1,3 poor. A cloud that formed later is carbon, 1,3 rich. Our solar system, at about 4.6 billion years old, is on the rich end. 3I, Atlas, is not. Working backward, through models of how the Milky Way's chemistry evolved, the research team, led by astrochemist Martin Cordner of NASA's Goddard Space Flight Center, estimated that this object accreted somewhere in the range of 10 to 12 billion years ago in a cold, heavily irradiated, relatively metal-poor cloud, most likely in the aftermath of an intense burst of early star formation. The paper was published in Nature on the 22nd of June 2026, after peer review. Set that against the numbers you already know. Our solar system, about 4.6 billion years. The universe itself, about 13.8 billion years. If the estimate holds, the ice in this comet froze while the galaxy was still assembling itself, and it never got warm enough to be rewritten, not once. Not in 10 billion years of drifting. There is one more twist in the Webb data that almost nobody covered, and it is the best evidence that this object was behaving like a comet rather than like a machine. Between August and December, its atmosphere changed character. The carbon dioxide to water ratio dropped by roughly a factor of 7. Carbon monoxide climbed. What started as a carbon dioxide-dominated coma became a carbon monoxide-dominated one, with a likely water-dominated phase in between, right around perihelion. That is exactly what you expect when different ices reach their boiling points at different distances from a star. It is the object cooking, in sequence, according to physics we already understand. Now for the part this channel exists to do. How solid is the 12 billion year number, really? The honest answer is that it is a strong inference, not a measurement. Nobody put a probe on this comet. The dating rests on models of galactic chemical evolution, and those models carry real uncertainty. We do not perfectly know the star formation rate across the galaxy's history. We do not perfectly know the yields from dying stars. And there is a second problem. The carbon, 1,3 content of the galaxy, also varies with distance from the galactic center, not just with time. So a very high 12C, 13C ratio could mean very old, or formed far out in the galaxy, or some combination of both. The Nature team is explicit about that. Their tightest reading, assuming an origin in the nearby galactic disk, points to 11 to 12 billion years. Loosen the assumptions and the range widens. There is an independent line of evidence, and it agrees, roughly. Before Webb's isotope work, other researchers estimated a kinematic age from the object's velocity through the galaxy. Objects that have been bounced around by the Milky Way for longer tend to move faster relative to local stars. That method returned a range of about 3 to 11 billion years, broad but overlapping. And it comes with its own hard limit. You cannot trace an orbit backward more than about 10 million years with confidence because gravitational encounters make the path chaotic. Two very different methods, one chemical and one dynamical, both landing on old, that is meaningful. It is not the same as a date stamp. Other groups check the chemistry too. A team using the European Southern Observatory's Very Large Telescope, led by Cyrielle Opetom of the University of Edinburgh, found elevated carbon and nitrogen isotope ratios in cyanide from the same comet. A separate ALMA study found the same deuterium enrichment in water. different telescopes, different molecules, different teams, same direction. That is what independent confirmation actually looks like. And the basic physical description still has soft edges. We do not know how big this thing is. Hubble observations through the 20th of August 2025 could only bracket the nucleus between about 1,400 feet and 3.5 miles across. That range is embarrassing until you understand why. A bright coma of gas and dust wraps the solid core and hides its edges. Measuring the rock inside the cloud is genuinely hard, which brings us to the question that dominated the internet for a year. Was any of this artificial? The evidence says no, and it says it from several directions at once. The trajectory followed gravity, with only the small perturbations expected from outgassing. Rubin found no unexplained acceleration in the early data. The activity profile matched comet models built from decades of observation. The molecules detected are standard cometary molecules. The coma evolved in the sequence sublimation physics predicts. Every instrument that looked, and there were many, returned data consistent with a natural body. What the isotopes prove is not that this object was built. It is that it was not built here and not built recently. And that is the more interesting result, if you sit with it. By the time Webb finished, 3I, Atlas had become one of the most heavily observed objects in modern astronomy. NASA's Spherix mission found water ice absorption and a carbon dioxide cloud stretching at least 216,000 miles from the nucleus. TESS, a telescope designed to find planets around other stars, was redirected in January 2026 to study the comet's activity and rotation. Hubble came back in November 2025. Parker Solar Probe watched it near the Sunday Punch tracked its tail. Spacecraft that had no business being comet observatories joined in. Psyche on its way to an asteroid, Lucy on its way to Jupiter's Trojans, Europa Clipper, Maven and the Mars Reconnaissance Orbiter from Mars orbit, and the Perseverance rover, which stopped driving long enough to photograph it from the surface of another planet. Europe's JUICE spacecraft, currently en route to Jupiter's icy moons, used 5 of its science instruments to observe the comet through November 2025, coming within roughly 0.4 astronomical units of it on November 4. None of that was in anyone's mission plan. 3I, Atlas passed Jupiter's orbital neighborhood in March 2026 and is now outbound, fading, moving back into interstellar space at the same speed it arrived. Ground telescopes tracked it as long as they could through the spring of 2026. Eventually, the light runs out. It will not come back, and no instrument we currently have will ever see it again. Meanwhile, the telescope that photographed it by accident finally went to work. On the 30th of June 2026, Rubin Observatory formally began the Legacy Survey of Space and Time, a 10-year program to image the southern sky over and over, night after night. Its whole design philosophy is that you cannot predict when something rare will pass. You can only make sure you are already watching. The Chandler team made a quiet point in their paper that has stayed with me. If the validation survey had begun a little earlier, and if the moving object pipeline had been running, Rubin might have discovered 3I, Atlas itself. It missed by days, not by capability. Think about what actually happened here, stripped of the noise. A cloud of gas somewhere in a young Milky Way collapsed and froze in the cold and the dark, before there was a sun, before there was an Earth, before there was carbon enough in the galaxy to make much of anything we would recognize. Some of that ice clumped together, then something threw it out of its home system, and it drifted, alone, through a galaxy that kept changing around it while the ice itself did not change at all. It crossed a distance we have no honest way to picture, for a length of time that dwarfs every human institution, every species, every mountain range on this planet. And then it passed close to one ordinary star. At the precise moment when the third planet around that star happened to have a 3,200 megapixel camera on a mountain in Chile, a spectrograph a million miles out in space, and roughly a dozen robotic probes scattered across the solar system, all of them capable of turning and looking. Researchers have compared it to finding a message in a bottle that has been drifting for billions of years. The ocean is the galaxy, the bottle is made of ice, and the window to read it was a few months wide. We got a piece of chemical history from a time and place we can never travel to, and we read it in time. So what actually changed? Before 3I, Atlas, we had 2 interstellar visitors and almost no chemistry. Now we have a detailed isotopic profile from another corner of the galaxy, confirmed independently by multiple observatories, showing water ice that formed below roughly minus 400 degrees Fahrenheit in a strongly irradiated cloud, in an environment poorer in heavy elements than our own, and older than our own. It tells us that the cold, ice-rich conditions needed to build comets and eventually to deliver water and organic material to planets existed in the galaxy far earlier and in less enriched environments than many models assumed. What we do not know is still substantial. Not the object's exact size, not its parent star, which may no longer exist. Not its age to better than a couple billion years. Not whether it is typical of interstellar objects or another outlier, because a sample of 3 is not a sample. That last gap is the one Rubin was built to close. If the survey performs, the count of known interstellar objects should stop being a historical curiosity and start being a population we can study statistically. The lesson underneath all of this is not about telescopes. It is about readiness. The biggest result in this story did not come from searching harder. It came from having instruments good enough, running often enough, that when something 10 billion years old drifted past on an ordinary Tuesday, the shutter was already open. Tell me which piece of this landed hardest for you. The object sitting unnoticed in test images 10 days early, the tail pointing the wrong way, or the ice that froze before the sun existed. I read the comments, and the best questions there tend to become future episodes. This is Beyond the Signal. Keep looking past the obvious.